Welcome to the intersection of technology, cybersecurity, and society. Welcome to ITSP Magazine. You're listening to a new episode of Stories from Space podcast, where your host, Matthew Williams, examines the history of human spaceflight, the breakthroughs that revolutionized our understanding of the universe and our place in it, and the brave individuals who work tirelessly to advance the frontiers of our understanding. Knowledge is power, now more than ever.
The authors acknowledge that this podcast was recorded on the traditional, unceded lands of the Lekwungen peoples.
Welcome back to Stories from Space. I'm your host, Matt Williams, and joining me today is Caroline Piaulet from the University of Montreal. She's an astrophysicist, a science communicator, and she's a researcher with the Trottier Institute for Research on Exoplanets, which goes by the acronym IREX, out of the University of Montreal. Caroline, welcome aboard.
Thank you for having me, Matt. Yeah, so I work at the Institute. Another thing that I'd like to mention is I also started a nonprofit to get kids into scientific research called Initiations. And that's something that we just started last year and that I'm very excited about as we talk about exoplanets, because some of my mentees in this program this year are actually working with James Webb data. Initiations is not a French word, but it stands for like initiating kids to science. And it's a nonprofit I started with colleagues about a year and a half ago.
Caroline, I recently came across your very impressive body of work when I was writing an article for Universe Today, and it had to do with how you and your colleagues were using telescope data to search for the elusive planets, exoplanets, that are between Earth size and Neptune size, where, as I understand it, there's a bit of a deficiency, or a bit of a, statistically speaking, they're kind of lacking.
Yeah, so one of the big surprises with exoplanet science was the discovery that planets we found the most of were planets that had sizes intermediate between that of the Earth and Neptune. And so just to give a little bit of context, in the solar system, we have the rocky planets and the Earth is the largest, and we have the gas giants, the gaseous planets, and Neptune is the smallest of these. And so we don't really have a planet in between. But most planets that we found around other stars, most other exoplanets, actually had sizes between the Earth and Neptune. And we can't really have a great idea by first principles of what they're made of. So we call the ones that are a little bit larger than the Earth the super Earth, and we call the ones that are a little smaller than Neptune the mini Neptune. And as you said, there is this dearth of planets between super Earth and sub Neptunes, which we call the radius valley. And we think it's due to planets basically turning from mini Neptunes into super Earth once they lose all of their gas. Fascinating.
And in fact, you developed several methods, and this came up in the study, to look for these planets, yes, in data obtained by space telescopes. Can you tell us a little bit about that?
Yeah, right. So the information we have about these planets is usually very sparse. For most of them, we really only know their size. And to know that, we use space telescopes mostly that look for a little blip in the light we see from the star that just comes from the shadow of the planet passing in front of it periodically as it goes around the star and kind of blocks it from our point of view. From that observation, which we call a transit, we can get the size of the planet. And what we did in this study was try to get one step further and constraining what the mass of these planets are. And the trick is, if we want to understand what a planet is made of, the size is not enough, right? It could be made of a lot of gas or a lot of rock. But once you at least get the bulk density from the mass and the size of the planet, then you can start inferring what it's made of. The challenge here was that the planets in our study are planets that are quite small and further from their star than the planets we typically study. And so it was harder with conventional methods. It was actually not really doable with conventional methods of mass measurement to get the masses of these planets. So we actually used transits to both measure the size of the star, the size of the planet and their masses using what we call transit timing variations, which we can go into if you're curious.
Oh, absolutely. Yeah. I mean, the methods there. So at first you were describing what my listeners may recall from a previous podcast. It's the transit method. Yeah, monitoring stars for periodic drops in light. And it's by far one of the most popular methods used to date. Now, when you said conventional methods for determining mass, were you referring to the radial velocity method?
Yeah, exactly. So the idea of radial velocity is you're looking for the wobble of a star due to the presence of a planet, right? The planet makes the star move a little bit towards us and away from us periodically, and that's what we detect even if we can't see the planet. The trick is that if we're looking at planets that are not very massive and that are quite far from their star, this wobble becomes really small and very hard to detect. And so then that's why we're happy if we have another alternative to measure the masses of these planets, like transit timing variations. And so the idea there is that we rely on the fact that there is more than one planet around the same star. You can't do this if there's only one planet. And so in the case of the system I was studying in this paper, the system that's called Kepler-138, we have 3 planets, planet B, C, and D. And the interesting thing is that they quite frequently get pretty close to each other. And so they perturb each other's orbits in a way that their transits, instead of occurring at precisely regular time intervals, sometimes happen a little earlier or a little later because they got moved by the other planets a little further or a little closer to the star. And that's what we can use to say, okay, was this planet perturbed by a planet that's 2 times the mass of the Earth or 3 times the mass of the Earth, and infer the masses that way.
Well, that's very, very interesting. Another takeaway was that you're able to obtain spectra from the atmospheres of these exoplanets as they transited. You've done a considerable work on this, haven't you?
Yeah, so that's another thing that you can do with the transit method is instead of being interested in the light that's just being blocked by the bulk of the planet as it passes in front of the star, you can look for the tiny amount of the star's light that was actually filtered through the atmosphere of the planet during the transit. It's kind of acting as a backlight, the star, and so you can see kind of through the atmosphere of the planet and then identify the imprints of the different molecules that would be there and that would cause different signatures in what we call the transmission spectra. So it's, if you observe kind of a rainbow, that's a spectrum, that's light broken apart into its different colors. So we do the same for the spectra we observe for exoplanets. And if we see that some colors are missing, then that tells us that they were absorbed by certain molecules, which then we can identify as coming from the planet's atmosphere.
Now, in fact, this is what you did for the study with the Kepler-138 planets. You were able to obtain spectra that indicated that some could be water worlds?
So the spectra we got for this Kepler-138 study were actually very preliminary. It was the first time we were getting spectra for these planets. And because they are really small, even if there is water or methane or things like that in the atmosphere, it would cause tiny features that we weren't able to detect. So the only thing we were able to say from the spectra of this planet is that it wasn't your typical hydrogen dominated atmosphere, which we think of for the gas giants of the solar system. They're made mostly of hydrogen and helium for their gas part. So we were able to say that it was not the atmosphere of a planet that would be made mostly of hydrogen and helium and just not have any clouds in it. But the water inference came from another route, which was the fact that these planets are both quite small, but their mass is also very low. And it's so low that it can't be just rock, like the typical super Earth. But also the planets are so small that if the gas was hydrogen helium and not something like water, it would be stripped away super fast by the star because less than 0.1% of the planet's mass would be in this gas form. And so it's kind of an Occam's razor argument. I would say that it's quite unlikely that we would be seeing not just one, but even 2 planets in the same system that have these low densities that show that they're not made of rock. But at the same time, we would have to be in a very fine-tuned scenario to be observing both of them at the cusp of losing the rest of their gas while they're having vastly different levels of irradiation they receive from the star.
So in terms of looking ahead, now your doctoral thesis was on how transit data and eclipse spectroscopy can reveal the details of an exoplanet's atmosphere. And this would be very, very useful for Spitzer data, Hubble data, and of course the James Webb Space Telescope, right? So I took from
Right.
that, yeah. Now this is an algorithm that you developed?
Do you mean inferring like the atmospheric composition of planets from this type of data?
Yeah.
So the basic algorithm is there and used by many scientists. I think what each of us does or do is that we try to incorporate extra levels of complexity to be able to explain increasingly precise data. Just to give you an example, the data we're now getting from the James Webb Space Telescope, we realize that we can't just assume that planets have the same composition everywhere around their surface. We have to take into account their kind of 3D-ness, their 3D aspect, the fact that they could have different temperatures and different compositions in different places. And the basic algorithms we used so far made these basic assumptions that were fine when the data didn't really grant more than that. But I'd say most of our work right now is incorporating more and more of this complexity into the way that we model atmosphere, into the way that we predict the signatures of different molecules and different temperatures in the atmospheres of exoplanets. And then seeing how this maps out when we compare that to data. So I didn't invent transmission spectroscopy at all.
Oh, no.
I'm just using it.
Yes. But this was the subject of your doctoral thesis, right? How to build on that and how to help constrain the search for habitability.
Yeah. So in my doctoral thesis, I'm doing quite a few different projects, and I'm interested in different types of planets. And the idea is that we want to understand better the way that they form and the way that their atmospheres form, the way that they accumulate gas over time, and kind of where they accumulate it, where they end up, the whole kind of history of an exoplanet as you can infer it, or to the extent that you can infer it from its present day composition. One of the other projects that I did earlier on was on a planet that was very, very close to its star. It had the size of Jupiter, but its mass was only a tenth of that of Jupiter. And so for us, that was very surprising. It meant that it was made of so much gas and so little rock to kind of accumulate all that gas. And it's this type of study that really motivates us to think differently about how planets form and where they form, where they accumulate gas, and what we can tell from that by looking at a planet today. Like if you look at the atmosphere of a planet today, how much can we really tell about what it's been through in its current chemistry?
Oh, yes. In fact, I have a lot of questions, which I won't bring up now, but just the idea that gas giants could become, that they would migrate, that they would be sitting next to their star. And what happens to them then? Do they blow off their outer layers and become rocky planets? You know, stuff like that.
Yeah,
it's rhetorical.
It depends. It depends on the planet, right? The idea is that, of course, if a planet is blasted by stellar radiation, it's going to lose some gas. The question is it going to lose it fast enough that it's quickly going to lose all of its atmosphere? Or over the star's lifetime, is it going to lose just 1 or 2% because it had such a high gravity? So we have these different kind of species of exoplanets, the ones that would lose all of their gas if they were put very close to the star, and the ones that would hold on to most of it no matter what.
Okay. Now, since joining the Trottier Institute, you've also developed a new method for how to determine atmospheric temperatures based on emission spectra.
So this is a method that for now we've only used on high resolution data taken with telescopes on the ground of the atmospheres of exoplanets, but it was meant to be potentially used for James Webb data as well. And it's being like in the process of being used for that too. So you need a high quality of your data, but the idea of this method is that instead of imposing that, for instance, the temperature is constant throughout the atmosphere of the planet, or that the temperature profile, which we call like, it's like the temperature as it varies with depth, has a certain shape that we just like conceive. Okay, it could be like straight and then increase with depth. Like as you get deeper, it gets hotter. Then instead with that method, you're able to get the temperature directly from the data. So it's using data of what we call the eclipse. So when the planet passes behind its host star, and because of the light we're missing then, like we saw the planet before and after that, while it's passing behind the star, we don't see it anymore. We can see how much light it emits in the different colors, in the different wavelengths, what we call them. And the idea is that from this, you can infer at the different depth of the atmosphere that you're probing with these observations, what the temperature is without making these kind of ad hoc assumptions that were made before.
Okay. Now, one more question there. I want to get into your efforts there with Initia Sciences and also the ones you've done before, like La Code de Science or Spring de Science. How that all sort of connects there. Yeah, well, I'll ask you that in a second there. But first off, so as an exoplanet scientist, how excited were you when the James Webb Telescope took to space?
Extremely excited and partly frightened that something would go wrong with the deployment or how it would get there, or that the data wouldn't necessarily be as great as, I mean, so many scientists and engineers have worked on that, but I think there was a lot of enthusiasm and at the same time kind of crossing our fingers that everything goes right. So when we saw the first images, the first spectra taken by James Webb, and we found it was even better than what was planned for, I think it was one of the best surprises and one of the best moments also. You know, we were like all together at the Institute watching these first images together. It was really special.
Yes. I mean, how could it not be, right? It's after all that time, after all those delays and cost overruns, it was like the worst thing that could happen now would be an accident. No, it was a total success. No hitches. Great. Wonderful. Yeah. Now, in terms of most importantly, what do you expect to come from this? Because given its abilities, given how it can directly image exoplanets, unlike previous missions, its high resolution, its sensitivity, what do you expect and hope to see come from this mission?
So I think talking about exoplanets, the most we're going to see come out of this compared to previous telescopes is actually for planets that we still can't image, but we can still study their atmospheres during transit and eclipse. But we can do these much more detailed analyses. Just to give you an example, because I worked a lot with Hubble and Spitzer data also in the past. When we only had Spitzer and Hubble, the most we could tell about a planet's atmosphere is that it had some water and it potentially had either methane or carbon monoxide or dioxide, which we didn't really know because we had like one data point that was just, if it was a little higher, you would say there would be carbon monoxide. If it was a little lower, you would say there wouldn't be. But what's really changing here with the Webb Space Telescope is that molecules don't have just one feature, one data point. They really have these specific fingerprints that we couldn't see with the existing data because the resolution wasn't there. But as we're looking at the transmission spectra from these new data, we can really resolve very precisely the different features of a given molecule. Instead of just seeing one data point, we're going to see the entire shape of the feature that we would be expecting. And that's, I think, what makes it most special is that we can first unambiguously detect these species, which before was kind of a question mark for some of them. We're also going to be able to say a lot more about the clouds that are in the atmospheres of these planets. That's also really interesting because it tells us how much of the light from their star they reflect, what are the species there. And specifically, I mean, probably most interestingly for me personally, and if you're thinking about the search for life, Webb is going to be the first observatory actually able to probe for atmospheres that are not just hydrogen, helium with traces of other things, but that could be made of mostly water, mostly methane, or like the Earth, mostly nitrogen with a little bit of CO2 or things like that. So I think that's probably the the most exciting part is kind of entering this new regime of atmospheres that we couldn't even detect before, and seeing whether they exist anywhere else than in the solar system.
That was the reason behind one of the test images taken by Webb, right, of the WASP 96b. It was to, as I understand it there, it was to demonstrate that it could obtain spectra and detect chemical elements. Now, did this demonstrate that it was able to do something that previously astronomers haven't been able to do?
Yeah, so just an asterisk here about what we were saying before. So WASP 96b is a gas giant that's made mostly of hydrogen and helium for its atmosphere, but it has water in its atmosphere, even if it's not in large amounts. And so what the first Webb spectrum of this planet showed is actually the features from the absorption of water. And if you look at the image, I know this is just like audio, but if you look at the image, you can see that you see multiple bumps, and each of these bumps is part of the spectral fingerprint of water. What we should remember is that before, when we only had the Hubble Space Telescope, at best, if we had good quality data, we would see one of these bumps. And so it's really kind of being able to unambiguously tell this is water that we're looking at. It's not just another molecule that would have an overlap in its absorption at the same place. It's just really this extended signature that's exactly where we expect it to be.
Well, it's good that they annotated it for us dummies, But yeah. So quickly, what I wanted to discuss with you next is your science communication, your outreach. Now, you have led workshops through what was known as the Spline de Science.
So the idea is like, we call them like science sprint. It's kind of the idea of we are with high school, the equivalent of high school kids for an hour, and we go with them through the steps of the scientific method applied to a given science project. So one of the projects I did during my PhD involved detecting water in the atmosphere of a planet called K218b. And it was interesting because it's a planet that's in the habitable zone of its star. Then for one of these science sprints, what I had the kids do was walk through the different methods and look at the actual data, and they themselves were able to identify the water features. So the idea is to show them what research really looks like, what data really looks like, to get them to understand these things a little more, and also to empower them that they're able to do research, which I think is what all of my science communication is really centered around.
Oh, absolutely. Yeah. I've just spoken to many people who have been at this way longer than any of us, and it's all about lighting that fire. Yeah. So in terms of your latest, you mentioned earlier that this was what you had started doing recently. It's separate from Spline de Science, but somewhat related.
So it's called Initiation, the idea is to give an initiation to science. So in this sense, I mean, the basic goal is the same, but then the time frame is much different. It's not a presentation like an interactive workshop for 1 hour like the science sprints are, but it's really bringing teams of mentees into our research labs for a whole school year. So they do it as an activity on the side of school, and many hours every week, they come into our labs and actually do research with us. So for this first cohort, we're 5 mentors, and I have three girls, 3 mentees that work with me every week. And so they learn how to do computer programming. They learn how to analyze James Webb data and to make sense of all of this. And what we really want them to get out of this experience is beyond just a 1-hour conference, to have them really participate in the process of scientific research and have themselves a contribution to research before they even enter university. So that's our ambition with that. And so we have projects going on for a full school year, and then we recruit mentors again for the next cohorts.
So it would be fair to say part of this is about encouraging women and underrepresented people in the STEM fields and space and astronomy.
Yeah, 100%. 100%.
Yeah. I'm really happy that there are efforts like that going on. So anything else you want to add about upcoming projects? What are you working on right now?
Yes. Yeah. So what I'm excited about right now is going to the next stage of what I've been doing for this class paper that we discussed. So I was really mostly using the density of the planet to say, okay, it's fair to assume that we're not looking at planets with hydrogen, but it should be water or something else that has a similar density to water, like methane. But the way to really tell that unambiguously is to observe the same way in the image you're showing for WASP 96b, is to observe these spectral signatures of water or methane or ammonia or these different species that could be there, and really tell what these types of planets are actually made of. So I think that's probably what I'm most excited about moving forward, is confirming that these planets called water worlds exist, and whether they are really made of water, or is it something different that we're not expecting. And this will only be able to tell for now with the James Webb Space Telescope. So that's something I'm really hopeful about in the future.
Yes. In fact, yeah, water worlds are kind of a big mystery, aren't they? They've got, we've never seen them until recently in exoplanet studies. And yeah, there's so much more we need to learn about them. And they do have implications for habitability too, don't they?
Yeah, because if it's actually water that we're looking at, even if for some of the planets the water wouldn't be in liquid phase, but it means that some planets can actually be 10% water by mass. And imagine just putting that in a place where the water could be liquid. This means you would be looking at very, very deep oceans. We don't know yet whether that's a great environment for habitability, because like the oceans here on Earth are much shallower than this. But still, it's really exciting to think about so much liquid water. That's such a key ingredient to life here on Earth.
Yeah, would demonstrate that there is such a thing as too much, or maybe. We just don't know. In fact, you know what? I would love to have you back to do an episode exclusively on water worlds and what they could possibly mean, what they might look like, what form they might take, because there are many sort of theoretical types, right? Well, if you have time in your schedule, I'd love to chat with you more about that there. But yes, as always, you're busy looking for exoplanets. Not a lot of time to talk about them, right?
I already do a lot of science communication. I'd be happy to come back maybe in a couple of months or so, once I have maybe more data to talk about.
Yeah. Okay. Well, thank you so much for talking to us today. And to my listeners, be sure to check out the Trottier Institute for research on exoplanets to find out about all the interesting research that Caroline and her colleagues are doing there. And also be sure to check out Initiations to learn more about their education and outreach efforts. The links to the websites will be posted in the episode data. Really appreciated having you on, and we hope to talk again soon. Thank you, Caroline.
Thank you for having me, Matt. Have a good day.
Thank you for listening. I'm Matt Williams, and this has been Stories from Space.
We hope you enjoyed this episode of Stories from Space podcast with Matthew Williams. If you learned something new and this podcast made you think, then share itspmagazine.com with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our podcast channels. We hope you will come back for more stories and follow us on our journey. You can always find us at the intersection of technology, cybersecurity, and society.